Okay, thanks for to have a chance to give a talk. This is part of my PhD study with my supervisor Shen, Dima, and Harun and Simon. And we'll talk about what happened to the ENSO in our ACCESS-CM2 and compared to the AGM, the middle office model. Before I started, just quickly give some knowledge what I'm going to present in this talk. First, I will talk about more about the ENSO life cycle. The other thing is the beyond feedback. Usually we use a Fourier transfer, to show the spectrum something, but nowadays we try to use the ENSO matrix from Clevat, and it's just like a easily to calculate the autocorrelation on the Neo 3.4 and then have like a 2 years lead and 2 years lag and showing on the right hand side. Can you see my mouse?
Yeah.
So in here to show the ENSO life cycle. So you can see the black curve that's from the observations. The two lowest points that represent the ENSO period. So it's about like 4 years, and the blue curve that's from the middle office one, the HGM3, that's also about like 4 years. But if you look at the red and green, the lowest point you can see actually pretty short. It's like about like 2 years. So somehow in our model and the Courier model, our ENSO period shows pretty short, only 2 years only. We did another plot analysis where you look at the ASC.
Arnold,
yes.
What is KACE?
Oh, that's Korea model.
The Korean coupled model or what?
Korean, yes, couple model. That's all the one we submit to CME6 this time. Yeah.
Okay.
Yeah. I'll talk about more the model thing in the next slide. Yeah. The beyond we calculate beyond feedback or the ASC coupling. That's calculate the correlation between Neo 4 zonal wing vs the Neo 3 SST. Here they show you the region of Neo 4 and the Neo 3. That's a monthly thing. So in here we can see the correlation coefficient showing here the black curve that's from the observations. This correlation coefficient is supposed about like at least 0.6 something. This all remains, and then when the ENSO happened, I will pick up to like 0.9. So that means Neo 3 and Neo 4, the wing and SST is supposed to be like a couple or talk to each other throughout the year. And the same thing happened in the HGM model. That's in blue curve, slightly come down, but still remain pretty good. But when you look at our model, the red curve, and the Korea model one, that's a green curve. Somehow in May and June, these two models, the wing at the Neo 4 or Neo 3, and then the wing at Neo 4, somehow that's decoupled. It's not like to each other. So yeah, that drives us interest to try to understand what's going on. Okay. So before I show more things, there's one thing I really want to emphasize. That's the paper from Fei-Fei's group published like recently. In the real world observations, before and after the 90s, the ENSO period did change from like 4 or 5 years, changed to like 2 years something. And also my previous paper also mentioned like the CP ENSO, the one focus on focus on the Central Pacific, that one is more like 2 years period, and then the traditional ENSO is more like 4 or 5 years. So the 4 or 5 years, 2 years ENSO did happen in the real world. And the right hand side, that's the figure from their paper. Don't worry about the vertical ones. We look at the x-axis. That's ENSO period. So it's like 2 years, 24 months. 36, so like 3 years, 4 years, 5 years, and up to 6 years. I circle up these ones. That's most of the model in here. You can see it's about like 2 years, 3 years, 3.5 years, something like that. And we are sitting in here. So I think like we are done alone. Still, I think more than a quarter of model from the CME6. I'll still perform the ENSO in like a 2-3 years period only. So there's nothing really dramatic wrong with the 2 years ENSO. Yeah. because a lot of people, I heard a lot of people say, okay, yeah, the ACCESS-CM2 is really bad in the CM2 in the ENSO simulation, but no. We catch one type of ENSO maybe, but okay, I'll go more details.
Wait, Arnold, can you,
Yeah.
so how do you say that the model, the observed, is 2 years? Because it peaks at 36 in the one period and it peaks at 48 in the other period. How do you get to 2 years?
No, okay.
It looks like it's no way 2 years. It's definitely 3 to 4 years.
Yeah. Okay, yeah, that's a good point. Because they use 3.4 index. But if you look at my paper, if you break into NEO 3 and NEO 4, NEO 4 will show you 2 years period.
And what is on the y-axis here in the right graph?
The Y. This is not my topic, but okay. Their paper is mostly talking about the North Atlantic will drive the Pacific, drive ENSO. So how much like a league on lake between the Atlantic to the Pacific that will alter the ENSO period. But that's not our main issue here.
And none of these points is the observed. There's no observed point in there, or is there an observed point in there?
It's red in here. This one, yeah.
Ah, the red one. Okay.
Yes. But again, this is I just want to show like within most of the SIMI-6 model, we are sort of sitting here. There's another bunch of models sitting there. So yeah, we are not alone. Yeah, maybe we only simulate one type of ENSO.
So Arnold.
Yeah.
I know what you're trying to get at. You're trying to say CM2 is kind of doing this one thing that it's not as good as it could be.
Yeah.
But I think it's important to note that CM2 is kind of in the 7 metrics that are available under the Clever ENSO metrics package. 5 of those, CM2 is doing better in 5 of those than the earlier ACCESS version.
ESM, yeah.
But there's also a second observation point, which is at 36 and 8 on that graph. It's just along from CM2. I think that's.
They have a different period. Yeah.
Yeah, I think that's enough observation point. It's not quite clear because you've got the yellow box behind it.
Yeah.
Yeah.
So that basically whatever that 8 leading months from North Atlantic is, which is not quite clear. That's that 36.
Don't worry. Yeah, this is not my concern in this talk. Yeah. My concern is just the horizontal, the X. Yeah. Okay. Let's go to the next one. My research only focused on these 3 models: our ACCESS model and the Korean model KS, and then the HGM 3.1 low resolution. I think we use exactly the same setting of the atom field part. This time we don't really have time to tune this model, so we just get whatever from Meloffice. We don't tune it. Only different part is the length surface. In our ACCESS, we use cable. Compared to the others, they use the jewels. The main difference is ocean model. Mount 5 and Mount 4 is pretty much similar, not too much different. I won't really alter the ENSO period based on our previous experience. The main difference is the HGM. They are using the NEMO. NEMO have similar horizontal resolution, but the vertical resolution is much different. And also maybe like Shifan can mention that in their model, they play a lot in the mixing layer, mixing skin, and they use a different mixing skin compared to our mount. Yeah, so maybe that's another reason I will cause the ENSO behave very different. But still, this is not really in this talk. That will be in the future next time. Yeah, I'll talk about that in the future research. Okay, so we only focus on these 3 models. Yeah. Before I started, just want to just close everyone. You can attention like if you like standing at the NEO 3 regions, and try to see like what drive you, like what the SAC. The SAC will be the shading contour, and then the contour, the blue contour, that's the precipitations, then the positive and the negative in the green contour line, and then there's the wind stress, wind speed showing in here. So like if you're standing at the new 3 regions, and then you can see from the observation, you pretty much this is the, like everything regrade onto a new 3 SST. So you can see everything's confined along equator and warming at the Eastern Pacific, and for the precipitation also confined along like 10 to 10 north and south, pretty wide, and then the zonal corridors, zonal wind also like along the equator. The width is probably like from from 5 south to 5 north. But when you look at the CM2, you can see from the SST regression pattern, we can see it's also along the equator, but at the Central Pacific here, we are slightly being squeezed southward compared to observations, and sent to the precipitation, the blue curve, you can see also being squashed downward, like more like moved from the center to like a southward, 5 degrees southward shift. And sent to the zonal wind, you can see the zonal wind also like a shift from the equator to like a 5 degrees south, and then become pretty narrow compared to observation. So from here, majority they say like in CM2 at the new 3 regions, we have like sort of similar pattern to the observation, but not exactly, because see like in the Central Pacific region we have like big difference. But when we move to the next slide, when you just move away from NEO 3 to the NEO 4 regions, so you can see this again, the shading is SST, the contour is the precipitation. But from here you can see in the observation, we still can see the SST is still confined, and everything is confined along the equator. The wing also pretty wide along the equator. But when you look at the CM2, the CM2 SST is like a moving, have like a warming pattern from the Central Pacific, and then like a move along, extend toward like California region. Similar to the precip, you see also like a move like a 5 to 10 degree north compared to observations, sent to the, and we have like really strong meridional wind in the CM2. So you can see like somehow in our model in CM2, NEO 3 and NEO 4 response really different. In here I didn't show the HGM3 is the Meadowfish one. Meadowfish one is pretty close to the observation, but I'll show more something like I'll show some plot later. So that's a basic, yeah.
So totally missing the response in the Eastern Pacific here. That's you're getting the observations.
Yeah. So I say it's just sort of like a Pacific meridional, more like, so I have the warming in here and then the cooling in here.
Okay, so that's all that PMM. Yeah,
Sort of like PMM.
Okay.
Yeah. The pattern looks like PMM.
I would be careful with calling the winds a response. You're just doing regression, right, in the coupled model. So the winds are not the response. The winds are just there at the same time as the SST are there. Whether they are a response or forcing, you wouldn't know.
Yeah, you have to do lags to work out whether really a response. Whether you're getting some response.
But to me, they do not really look like a response to NEO 3 and NEO 4 SST. They look more like something that might have been forcing it or something like that. Or something happening in the northern hemisphere or something, but not necessarily something that is on the equator.
In this one, it's the index is the NEO 4 winds that is then being regressed against everything else, rather than NEO 4 SST.
Sorry. Yeah.
So it's NEO 4 winds rather than SST, but you're using as your regression. NEO 4 UAS, okay, regression patterns.
US, the US, at the NEO 4 region. So yeah, I did mention that. Yeah.
Okay.
Oh, sorry. Yeah, like NEO 4 zonal wind. Yeah.
Okay.
Okay.
Yeah.
So it's the NEO 4 winds you're starting with, and that's why you're not picking up the SST pattern across in the Eastern Pacific, because you're not using an SST as a starting point.
Yeah. Okay. Cool. That's a good point. I'll remember.
So that's
Okay.
probably why it's not surprising, because you're not even starting with an SST pattern. So the fact you're way over in the west of the Pacific means you've got very little connection. But it's surprising that the observations have such a strong response from the west right across to what's taking place in the SST.
It's sort of weak, but still pretty much, still.
But there's very strong weak winds right across there, but there's still a strong response, because that just means that's just there because that's the El Nino is still there, and that's because there was a really much stronger response on your previous plot in that region to start with, in that upwelling region to start with, because we really don't have a strong upwelling in that region in our model.
Okay.
We don't.
I'll go to the next one. So in this research, we do we use two model to do some experiment runs, try to understand. First one, want to test whether this ASC decouple is the one to cause that to cause the biennial things. The others we want to check whether it's because of the model mean bias, or maybe it's because of some the nonlinear turn or something, anomaly turn to cause that. So in this research, I used our model, the recharge oscillator model. Eventually, I see it's from DIMA. The main two equations from this is the 1 and 2. So that's in here is the T is the NEO 3.4 index, and H is the thermocline depth. And here it shows the temperature tendency. That's the equation. And then I always mention I have to thanks to DIMA. You guys make the equation looks easier to understand, just break into the A11, A12, A21, A22, rather than compared to if you look at the Fei-Fei's original paper, that's really like RF something that's pretty difficult.
That's actually not on me. I use the version from Burgers. Right?
Oh yeah.
So this is just
I found
his version. It's not my version.
Claudio did that, right? You did, yeah.
Yeah, but the upper equation 1 and 2 is original from Burgers. I didn't change anything to it.
Oh.
It's just the way that he has presented it.
Okay.
Which was nice and simple. And then
I always mention that's from you. Okay, makes
it's
not
for me. No, sorry, I would have liked to invent it, but it's not for me.
Okay, yeah. In here, particularly down to see the A11 can bring into the ocean part and the atmosphere part. So in here, so the ocean part and the atmosphere part, and from the atmosphere part can also break into the sun coefficient times the wind stress plus the ocean feedback in here. We are really surprised to we are excited to see this one, this coefficient. This coefficient is actually just the response between with the wind and the temperature. So we just play this C tau A, this the Bionic feedback turns. Yeah, in when long time ago when we just started, and then DIMA suggests we play this turn and then try to change this turn. And see how this model will change. So in here, clearly show the result. We have directly from the observations, the life cycle I showed the first slide, and also the CM2 that's also directly from the model, historical model. And then we have two experiments. One is if we keep everything, all the parameter, everything, coefficient, whatever, based on the observations, that's in the solid blue curve. And then the other thing is the one I just mentioned, the C tau A this turn. If we just change in May and June, because I showed before, in May and June in our model, the ASC somehow decouple. So we make just force this C tau A in May and June to be the 0. And that's the experiment to plug into the solid red curve in here. So you can see when we have the model, when we have the observation settings, this model give you about 4 years, 4 years, about 48 months period. But once we perturb this turn C tau A in May and June, And you can see this model, the period straight away change become like half. So you can see the lowest 2 points. So straight away the period shrink. So in here, just try to say that maybe due to the Biasini feedback decouple in May and June, that will cause the biannual ENSO in our model. And that's sort of proof from the recharge oscillator model. The next one we want to play is like try to understand whether it's from the mean state or the anomaly turn to cause the pattern looks different. So in here, eventually the first we have like a I use the historical round SST, so breaking into the confirmation turn and the anomaly turn, and from the CM2 and also the SAT from historical round from HGM3 and breaking to the climatology and anomaly turn. So eventually this one is the repeat the historical round from CM2, and this one is a repeat the historical round from GC3. And then the other two rounds like I shuffled. So like a GC3 climatology with CM2 anomaly, or CM2 and climatology with the GC3. And then all those SAC I forced into our atomic model, try to see what does it looks like. And here's the result again to show the Bianchi feedback. So you can see the result is pretty simple. Only the one with the CM2 anomaly SST will cause the decouple. The black curve in here is original CM2 from the historical round, and from here you can see this orange curve with the CM2 anomaly, or the sort of like greenish this ones, also with the CM2. Only these two with the CM2 anomaly, that SST at the NEO 3 and the wing at the NEO 4 will somehow decouple. And this the last slide I want to show, like I said before, in here just do the quick assemble of the SSC at the NEO 4 and NEO 3 regions. From the observation, you can see pretty much assemble contour will mainly overlap to each other, and either you choose NEO 3 or NEO 4. No matter how the SST pattern will pretty much overlap to each other, similar to the GC3. No matter you choose NEO 3 or NEO 4, the assemble SST will overlap to each other. But when you look at our model and compare to the Korean model, the NEO 3 and NEO 4 just totally separate. And NEO 4 in our model, in Korean model, somehow is like sort of influenced by something else. It's driven by some other things. So yeah, that's pretty much my talk for today. Yeah, Dima, you're mute.
Yeah, sorry, I just applauded.
You ended that.
Thank you.
Yeah, but to your last slide, it's interesting. So I wonder, in your experiments, you did these experiments, or can you redo them, or because I find it a bit strange that you put anomalies from the covered models, which are already very strange. Why not putting the anomalies from observed and then put them onto different background states? And because the anomalies are already very strange, right? I mean, you have very strange kind of patterns.
Yeah. Okay.
And if you want to test whether I've seen in the past people using different climatologies and then put the observed anomalies on top of it and see what happens.
Okay.
Or put an idealized observed ENSO pattern on it and then see what happens. And usually they show that the background state does do something to the coupling.
Yeah. Okay. I think that's a really good idea. I think maybe Shen will put it in the thesis rather in this paper. Yeah, I'll do that experiment, and then that's a really good idea. And Yunpa.
Thanks, Arnold. It's really interesting. And I just wonder, how do the climatology look different between CM2 and GC3? Oh,
that's a really good one. Yeah, that's a really good one. I may change the. Can you still see my?
Yes. We can just see the slide set that you were using, but it's out of presenter view now.
And you can see I'm looking for the paper, right?
No, we can still just see the slide set you were showing us, but it's out of presenter view.
Oh, okay. Maybe I need to share again, but give me 1 second. I'll find the figure first.
So Dietmar, I just want to come back to your question. I think we were kind of thinking because GC3 did it had a 4-year period like the observation. So it was what we used as like our target model, because it was doing everything that it was meant to do. And the only difference between CM2 and it was the ocean. And then we kind of went, well, you know, what's the difference between the two models? And that's kind of why we used, so you said you used the observed climatology, but we used the GC3 kind of, you know, suggesting it produced like an ENSO that was kind of realistic. That was kind of where thinking.
Yeah, but I think the anomalies look strange, right? I mean, you have very strange anomaly patterns. I'm not sure what they tell you. Because to me, it seems like you have a model that has a problem, that has something causing biases in the feedbacks, and they will obviously change the variability modes. But you're putting in these strange variability modes to figure out what is causing these strange variability modes is kind of not helpful. I would rather have the background state changes and then put in something defined that is realistic, like the observed SST modes, and then check what is this background state doing to the feedbacks.
Yeah. So yeah, I understand where you're coming from. It's just you're looking at things a different way to what we did, and I can see where you're coming from. So yeah, thank you.
I think we can do that. Yeah. I'll try to set up the round and then present that because anyway, I think Dietmar will ask the same question next year in the milestone, so I better do that now. Yeah. Okay, Yunpa, this is the observations of the SST perceived U and V, but that's only focused on May and June, the mean over the May and June. And the right-hand side, that's the bias. And we have like a CM2, KS, and then GC3. It's different, yeah, but it's different. But from our analysis, our experiment, it seems like not really driving everything different, not because of the mean state bias to cause the decouple. Yeah.
Thank you.
Okay, and Shifang.
I was a bit puzzled by these AGCM experiments, but perhaps this may also help because this is this May-June decoupling. How can the AGCM experiment with this different SST field in it still say something about this Birkenes feedback? Because surely the Birkenes feedback actually involves having a coupled experiment going on, or does it actually need a coupled experiment to actually have that going on? So, I mean, for me, even your simple coupled experiment, your simple coupled type experiment still needs this plot.
Yeah,
I was puzzled why that would still show a response even if you're just doing an AGCM, but that maybe I was missing something.
I just think because in here to prove the anomaly things, so I don't know. I think can we complain this is maybe because chicken and egg things, because anomaly turn, these anomalies generate from the couple model. So in here we just only to use this anomaly to show you by using these kind of anomaly turns will cause the model or the wind drive differently.
Oh, so you're just saying these anomalies are upsetting the winds rather than necessarily causing the Birkenes feedback. Okay, so because it's only just this part of, it's only part of the coupling because it's not the full coupling because so it's only that part of that Birkenes feedback coupling. Yeah, I guess I tend to think of the Birkenes feedback as the whole part of that couple.
No, just like NEO 3, NEO 4, that kind of tropical region only.
Yeah. I guess I'm not a simple couple model person. I'm a full couple model person. So I tend not to see it in that sort of way.
So we're almost wrapping up. For time wise, there's one more question. So Dietmar, I can see your hand up. I'm assuming because no one else has their hands up, there's no more questions. So over to you, Dietmar.
Okay, if nobody else has a question. So you showed also, so your model is too biennial, so it's has a period shifted, but it looked also to be too regular, right? So your cross correlation or your autocorrelation was too regular. And I think you showed nicely with the Richard oscillator model with the parameters when you take away the coupling in May, June, that you get the periodicity shift.
Yes.
But what is causing the model to be too regular? I mean, is that, have you tested that? I mean, so it's one thing is shifting the period, but also making this period really very regular and not as chaotic as we observe it. What is causing that?
I think that will be the next paper. We're still working on that.
Oh, okay.
Because like at the beginning we say the maybe the ocean, because you can see the main difference between these three models is the ocean part, right? So we the next time we're looking into the oceans and see if what will cause that. Yeah, but at this stage we didn't really focus on what caused that yet.
I would suspect we're missing some decadal variability, and there's an experiment going on at the quarter degree at the moment, which possibly is the experiment Matt's involved in. We seem to have tricked a little bit more decadal variability, and that's involved some changes Andy Hogg suggested, which into neutral physics. And so if we really think that it has tripped some more neutral physics into neutral physics, then we may put some similar changes in the neutral physics back into here. But let's see if we can analyze more.
Yep. All right. I'll stop here.